Okay, day 2, block 2 of 214. Ow, I hit my head. What we're gonna do is build on yesterday, and we're gonna do a couple of examples and all that jazz, whatever. In pharmacy and medical fields, you have what they call a particle spectrometer. And granted, it's far more complex than what we're going to talk about, but this is just a general idea. And then there is what we call a velocity selector. And these are typically put together in the same piece of equipment. The velocity selector allows particles of a specific velocity to pass. And what happens is in the velocity selector, you have, basically this is a expanded view of a pipe, and you have charged particles, let's say a negative particle and a positive particle, and they're moving with a specific velocity v. The first thing that they set up in these particle or velocity selectors is they set up an E field. And the E field, it all depends on how the setup is, but in our case, we're going to set up the E field to be from left to right, which means that the positive particle feels an electric force to the right, and the negative particle feels an electric force to the left. And that's because of the electric field. Charged particles feel forces that in the direction of the E field. If they're positive, they feel opposite in the direction if they are of negative charge or opposite charge. The other thing that they do is they set up a B field, and in our case, we're going to set up the B field to be into the page like so. For the electric field, you know that the force due to the electric field is just Q times E. What we do with the magnetic field is the magnetic force is QVB. And the direction of the magnetic force is Q V cross V. So for the charged particle that's positive, and actually for both cases, V cross B means that V cross B is to the left. I'm going to write it over here. With the positive charge, that Q is positive, and positive times a left direction means that the magnetic force on that positive charge is to the left. And because the negative charge has a negative charge, it's negative times V cross B, and negative V cross B is simply the opposite direction. So it is negative V cross B, or you could just say that that is the direction of the magnetic force on the negative charge. In both cases, what we want are particles, regardless of them being positive or negative, they could be positive or negative. In either case, they feel forces that are opposing each other. And we want a situation where they pass through these plates without crashing into the walls. Because if FB is greater than FE, or FE is greater than FB, they crash into the wall. If they don't crash, the sum of the forces in the x direction are zero. It's in a translational equilibrium in the vertical, which means it's not going from left to right. This means that in both cases, they're opposing each other. So I don't really care about the sign. All I care about is one is negative and the other one is positive, so that FE is equal to FB. Which means that QE is equal to QVB. Now this is one of the interesting points. If obviously the charge passing through it is equal to each other, so E divided by B is equal to the velocity. So if we had, let's just say, if E was equal to 10 newtons per coulomb and the B field was 0.1 Tesla, the velocity is 10 divided by 0.1, 100 meter per second particles would pass through that. If it was going too fast, the magnetic force would be stronger and positive particles would steer left, negative particles would steer right. If the velocity was less than 100, then the electric field forces would win and then they'd crash in the opposite direction. So in this particular case, this is an example of how B and E create force vectors that add together. So really this could be an example of a vector. This is kind of a simple vector addition problem. The electric force goes in one direction, the magnetic force goes in the opposite direction, and so in the end you get a net force of zero. And so this is an example of how electric fields and magnetic fields can work together. At the end of this velocity selector, the particles come shooting out at a specific velocity v, and the magnetic field in this region, I'm going to say is still into the page. It could be out of the page, it doesn't really matter. So what happens? Let's blow this up just a bit. So we have a region where the V vector is pointing to the top of the page, and the magnetic field is going into the page. Now these particles are entering the region. Now, there is no E field in this region. The E field was only in the velocity selector. But all of these particles have identical velocity. But they don't have identical mass, they don't have identical charge. So what happens? V cross B is a vector that's to the left, which means all positive charges bank left. And so what happens is that the charges bank left and they move into a circular situation, and then they eventually crash against this horizontal line right here is like a wall. Negative V cross B is to the right. So all negative charges bank right. Or a magnetic field is a great way to separate positive and negative charges. So if you had a stream of charges, and those charges were positive and negative, and you wanted to basically tell the charges, all the negatives go on one side, all the positives go on the other. You send them through a magnetic field. One of the particles that just doesn't care are the neutral charges. The neutral charges will just pass straight through and just not give a flip about what's going on. The neutral charges are unaffected. So it's not really good. Mass spectrometers and velocity selectors don't do anything with neutral charges. So on this plate, now what happens on the plate is you have some type of material that is sensitive to particles impacting that material. And so the material sends out a signal. The signal is picked up by a computer. The computer reads it or puts it out on a plot. And so you could see the spikes where large quantities of particles of a particular type hit. And dependent upon the material being sent through the mass spectrometer, you could figure out what the material is. These are semicircles. Let's just look at one. When it shoots through, the force, let's say that was a positive charge, that magnetic force is pure left. And what happens is that particle starts to curve in a circular fashion until at that point its velocity is straight down. It still feels the magnetic force, but the magnetic force is kind of flipped in the opposite direction. And so the magnetic force is a lot like is related to circular motion, and how radial acceleration, or v squared over r, will help you figure this out. If this is a circle, that is r, that is r, that is r, and the total distance d is 2r. So the total distance of that circle from the point where it entered the mass spectrometer to the point where it impacted the surface is a distance 2r. It's circular motion. So in circular motion, it's a circle of a constant radius, and because of this, you can say that the sum of the forces, which is equal to ma, is equal to mv squared over r, where r is the radius of that circle. The force being applied to this is QVB. QVB. Now D is equal to 2R, or D over 2 is equal to R, or 1 over R is equal to 2 over D. This right here, one of the V's cancels, and I'm left with 2mv over D is equal to QB. So that goes in there, and then one of the V's cancels, and I get this. So that 2mv over QB is equal to D. And that the distance is 2 times the mass times the velocity divided by the product of the charge and the magnetic field. So in this situation, we determined in the previous example that the velocity was 100 meters per second. Let's say the mass was 1 gram, or 1 times 10 to the negative 3 kilograms. Let's say that the charge was a positive 0.002 coulombs, and that the magnetic field was 0.01 Tesla, or 10 millitesla. So this becomes 2 times 1 times 10 to the negative 3. V is 100. Q is 0.002. T is 0.01. And let's hope that the numbers work out. So the distance, the distance is kind of big. 10,000 meters. It's a really big mass spectrometer. Typically the distances on those mass spectrometers are like on the order of millimeters to a few centimeters. So the numbers don't really matter. But let's just say that our spectrometer, we had a ton of funding that year, and we decided to build a multi-kilometer mass spectrometer, and that's how you would do it. So what this is really illustrating is circular motion, charges in a magnetic field. Earlier we saw how the forces added, the force vectors added, and so we end up with something like this. And we get that. Now the last thing really that we have in the homework for problem set 4 is we've seen how B fields cause freely moving particles to curve. Wire is a stream of negative particles, or really negative electrons, or just flat out electrons, kind of redundant. So we've got a stream of negative charges, and so if we had a wire of current I with no B field, that wire would just go on its merry way and not bend or anything. But if we had a B field present, let's say the B field was in, what would happen is that the current would cause the wire to bend in a particular direction. And this, what's really happening is that there is a magnetic force pulling on that wire in the upwards direction in this particular case, and the force on the wire is ILB. So the current times the length of the wire, current, and that is the length of wire, and then you got the B field. So let's do, what we're going to do is we're going to talk about the lab. In part of the lab, what happens is you have a wire with the current in this particular case, it's coming out of the page. And then it's resting on a scale. This is a magnet, and that is I out of page. Now the way that the B field, I'll have this thing set up, is that in this gap, the B field is from right to left. And what you notice is with no current, the scale reads whatever the force of gravity is of the battery sitting on top of the scale. The way that we have it set up is as I increases, the scale reads an increase in F sub G. What happens is that this new F sub G is equal to the old F sub G plus ILB. Now this wire is attached to a fixed mount, and when you turn on that wire, Newton's third law kicks in. There is a force on the wire and there is a force on the magnet. So what happens is that you put in the current and the B field interact. The B field tries to push up the wire, but the wire is attached to a mount. And so what happens is that instead of the magnet pushing the wire up, effectively the wire is pushing the magnet down. And what happens when you push down on an object? The normal force increases and you see a heavier weight. The scales, I always forget this word, and words are English, I don't really need it. They call it zeroed or tapered or whatever. The scales are zeroed. So you don't read FG, you only record the I's that you put through, and then these forces, or actually the force on the scale. So you read the force in terms of, it gives you a mass that you want it in kilograms. And this is what you do with it. You have current, you have the mass that's read on the scale, you have the force of gravity, which is really you just take the mass and multiply by 9.81, and that gives you this other thing. And what you do is you plot those two lines. You plot this as a function of that. And what happens is force is on the vertical, I is on the horizontal. You'll see something like this, and then you plot the points, and then you get a line. Well, F is equal to ILB. And this F is this F right here. I don't know if we call it F sub G, but F is good enough. And what you're going to do is you're going to rearrange this so F is equal to LBI. And you compare it to Y is equal to MX. I is the independent variable. F is the dependent variable, which means that the slope is equal to LB, or that the B field of the magnet is M divided by L. And that's how you get the magnetic field strength of your magnet. In part 2 of the experiment, what you do is I is constant, not continued, constant, while L is varied. So F is equal to ILB. You have L, and once again you do the same thing with, you read the mass, you convert it to force, you get all these data points, you fit the line, and what you determine is, rearranging this, F is equal to IBL, Y is equal to MX. So Y is the force, X is the length, and the slope of the line should be IB, so that the B field is equal to M over I. And what happens is that B and that B are identical because you're using the same magnet. In the first part, you're adjusting current with a changing, you're adjusting current with a fixed length. In part 2, you've got a fixed current but adjusting the length. The consistent thing is the fact that the magnet is the same. So you can push on it, pull on it, all that fun stuff, and you get these forces. Now, one thing that we'll do, because I enjoy talking about it, is I'm going to do an example with an E field, probably from the homework. And the first one, okay, I know what I'm going to do. The first one comes from, it's in the last problem set, and it's got 2 wires, and I'll change the numbers. And what I want to know is, I have a current going through here, the I is 0.8 amps. The current going through here is 0.1 amps. And then the distance from there to there, I'll call that L, and that is 0.2 meters. And what I want to know is, where is the B field 0? This problem was given to my class, or I made it, and then I gave it to the class, and I was like, let's see how they do on it. And there were 3 major groups of people. I'll tell you the first 2 immediately. There was the group that got it right, the group that got it wrong, and then the third group was actually the most interesting group of them all. So let's work through this. When you do this, the green line, I will say, is the upper line 1. And when you plot, or the first thing you want to do is you want to show the directions of all these wires. So we're going to use the wrap rule. Thumb goes left. Anything above the green wire goes into the page. Thumb goes in the direction of the current. Fingers go that way. So anything above that wire goes into the page. Anything below the wire is out of the page. The red wire is wire 2. Now its current is to the right, which means that anything coming above the wire is out. Anything below the wire is in. And I'm going to call these regions A, B, and C. So just by looking at this, which region you can just skip? You can skip one region, obviously, because it's never going to be 0, ever, 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 ever. Which region do you skip? B. Because both of the B fields are out of the page. Both are positive. Can you take a positive number, add up another positive number, and get 0? No. So B can just be skipped. You don't have to look there. Now both of these are infinite wires, and the B field for an infinite wire is mu naught I over 2 pi r. There are two regions that we now have to look, and one of these 2 regions, you really don't have to look at it at all. This wire has the lesser current, which means at a given distance, if I was to look at directly at a line directly in between it, the B field from wire 1 is less than the B field from wire 2. Why? Because wire 2 has a greater current. The closer I get to wire 2, I'm moving away from wire 1, which means that the B field from wire 1 is getting weaker as I'm getting closer to 2. So the B field from wire 2 is getting stronger as I move down, the B field from 1 decreases and the B field from 2 increases, because you're getting closer to the wire. On this side, as you're moving away, B field 1 decreases and B field 2 decreases. In this particular region, B1 will always be less than B2. And why is that? Because you're already a further distance away from a weaker wire. So if you're just on this side right next to 2, the B field from 2 is way stronger than the B field from 1. And the further you move away, granted the B field from 2 is getting weaker, but 1 is already weak to begin with, so you can ignore it. So really, you can skip C. Eventually, we'll go into group, or we'll hypothesize that it is in section C, and we'll see an interesting thing. So what happens is you just go, that is a distance X, and I'm looking for X. I'm looking for the distance above wire 1 where the B field is 0. The B field from wire 1 is negative, the B field from wire 2 is positive. So the sum of the B's is equal to 0, which is equal to minus B1 plus B2. So B1 is equal to B2. These are infinite wires. So mu naught I1 over 2 pi R1 is equal to mu naught I2 over 2 pi R2. And one of the things that I like about this particular problem is that I don't have to memorize mu naught. Why? Because they cancel. I can cancel the 2 pi's. And I'm left with I1 over R1 is equal to I2 over R2. Well, the I1s are given. I1 is 0.1. I2 is 0.8. R1 is the distance from wire 1 to the point, or X. So this is I1 over X. I2 is there. R2 is that distance and that distance, the distance from there to there, or L plus X. I have I1, I have I2, I have L. Find X. So I cross multiply. I distribute. I get my X's on one side. And I forgot my L. And then I solve. Oh, I keep the L. Li1 X I2 minus I1. And then I solve for X. Li1 over X I2 minus I1. So that gives me 0.2, 0.1, what am I doing? This is a great question. Solve for X, Li1, I2 minus I1. And you can look at this and go, that's not a distance because those distances cancel, those currents cancel. So this is what I'm looking for. 0.2, 0.1, 0.8 minus 0.1. And that gives me an X of 0.0286 meters. So roughly almost 3 centimeters above wire 1, the B field is 0. And that's the answer to the problem. what I'm going to do is, when I gave this problem, I did not expect the third category. The first group of people, they did it this way, they got it right, they got their points, and they left. I'm fine, I was happy with that. The second group of people just got it wrong, they didn't know what they were doing, and I expected that, and I was fine with that. The third group, what they did is they said, I don't think that the B field is 0 up here, I think that the B field is 0 down there. And so what they did is they said, so they got I1, I2, they still got L, but they said their X was not above I1, they said their X was below I2. And they went to find that value X, and this is a discussion of the third group. So they set up the problem the same way. They looked at the B fields and they saw that the B field from 2 was into the page and that the B field from 1 was out of the page. They said that there is a point below I2 where the B field is negative. So the sum of the B fields is equal to 0, which is equal to B1 minus B2. So B1 is equal to B2. Same stuff that we did before. B1, mu naught I1 over 2 pi r, mu naught I2 over 2 pi R2. Those cancel again. I1, I2. In this particular case, R2 is X. The distance from that wire down is X. The distance from I1 down is L plus X. Look for X. Solve for it. So we do I1 X, I2 L plus X, I1 X, I2 L plus I2 X. Get my X's on one side. I1 X minus I2 X is equal to I2 L. Solve for X. I'm sorry. Yes. X I1 minus I2 equals I2L, or X is I2L over I1 minus I2. And so this is the interesting part. I2 is 0.8, L is 0.2, I1 is 0.1, I2 0.8. And that gives me a number of negative 0.22, trying to figure, 86 meters. And it was a negative, quite clearly. And a lot of people looked at this number and said negative 0.2286 meters. I don't know what that means. And that was one of the groups in the third group that looked at that number and just went, I have no clue what's going on. But the second half of the third group did me so proud. That L is 0.2. When they had set up the problem, they had set up the fact that X was positive in the downward direction, which means that the upward direction was negative. So the answer that they were given, or that they showed, was 0.2286 meters, which means it was 0.2286 meters in the opposite direction. And if that distance is 0.2286 meters and that distance is 0.2, then that distance there is 0.0286 meters. Which is exactly what you would have gotten had you chosen the correct direction. The second group, the second half of the third group, recognized that the negative sign basically screamed at them, you were looking in the wrong section. Let me show you where it is. And so what they did is they got that number and they said, oh, if I deduct 0.2 from it, it's that distance right there. And they effectively took that number and correctly interpreted it. And I looked at that and I was like, wow, man, it was really interesting to see people make a mistake and take the numbers given to them, interpret them correctly, and then grow from it and understand what went on. So, and that particular group, if I could, the days of giving bonus points for a test are long gone, but I was like, man, I should have given them something. But they got the problem right. And so in this, what we've shown is how E-fields add up in a very interesting way. And then we also have shown how to do forces on magnetic fields. The next problem, actually now what we're going to do is we're going to do forces on a wire. And this problem I loved. I made it up myself. Maybe I stole it from somebody, but I don't know. It's in the problem set, and it's in problem set 4, and it's number 7, IC springs. Number 7 was given in the fall of 2010 as a test problem. A couple of years later, I was privately tutoring an individual in Cal-based physics, and I tutored him from Cal 1 through 4 in differential equations. And he said, I knew you before I even met you. And I was like, what do you mean? And he said, a lot of my friends, he was Navy ROTC, and when you're Navy ROTC, you have to take Cal-based physics. And so he said, after your first test, a group of them all got together and they all just sat down and cursed your name for hours. And I was like, what, for what? And they were like, for that problem right there, number 7, IC springs. Because they said, quote, I didn't think we had to remember anything from the previous semester. Because this was 212. Equivalent of 214. And they were like, I can't believe he had us try to figure out springs. I'm like, it's just Hooke's law. You gotta remember this stuff. In the unstretched position, I'm gonna say that the x is equal to 0. So this is the unstretched position. The wire, and in fact, now that I'm doing that, oh no, I did give, all right, I think everything is fine. In the unstretched position, it's this. With no B field, the springs with that additional mass of the bar stretches. And it stretches a distance 2 centimeters. The bar is 2 kilograms, or the wire. And so the first question that you got to ask is, all right, these are identical springs, but what is the spring constant of the spring? If I had simply asked you back in 213, you have a bar, you've got two springs, what are the tensions in the springs? And what is the subsequent spring constant? And you would say, well, there are two springs, so there are two forces, each of them giving a kx up. So the total force up is 2kx. The force down is just the force of gravity, which is just mg. I know that the bar is doing nothing. It's just sitting there. No magnetic field, no current, no nothing. And that means that there is a positive 2kx up and a minus mg down, which means that mg is equal to 2kx, or k is mg over 2x. The m is 2, g is 10, 2 and x, 0.02. Which means that the K constant is 500 newtons per meter. No, let's hold on. Let's do the calculation. 500, yes, I did the math. So that's the spring constant. Then I apply a magnetic field to it, and it stretches even more. So now the additional 3 centimeters, so the total length is 5. The current is going from left to right. And what do I know about the magnetic force? Is the magnetic force up or down? Is the magnetic force up or down? If you switch this thing on and the springs stretched even further, they're down because it got pulled down. So the magnetic force is down. The current is to the right. So what direction is the B field? What is its direction so that I cross B is equal to F sub B? Is it the B field left, right, up, down, into, out of? What is it? And this is one of the interesting things I'm kicking around for the right-hand rule. We should practice some later. We're so used to like A cross B is equal to blank, but how about if I do A cross blank is equal to C? We could do stuff like that. And this is an example. So if I chose I cross up, that would be kind of dumb because I cross up comes out of the page. And one of the students made an interesting observation that according to the rules that I've set up in the right-hand rule game, I use all 3 directions for every problem. If one is horizontal and the other one is vertical, that other one has to be in out. It's just the way that the vectors work. So you're the one who came up with that. So I have the current vector is left, right, or right. The magnetic force is up, down. So what choices do I have for the B field? It has to be either in or out. So let's do the wrong one. Let's say that B field was into the page. I, B, F sub B is up the page, which is incorrect. which means that the B field has to go out the page so that the magnetic force is down. And I've been teaching this for years, and I had completely not realized of the shortcut you could do. So left, right, top, down, which means we have a choice of in or out, and that's it. So the B field has to be out. Now, once the B field is on and the current is on, the bar stretches. It reaches an equilibrium, which means once again the sum of the forces, what is that? Sum of the forces is equal to 0. So let's talk about the forces. Let's talk about upward forces. There is the 2kx of the springs. In this case, the x is going to be 0.05 meters. There is the force of gravity, mg down. And then there's also the ILB down. Now, the question is, what is the strength and the direction of the B field? The direction is out of the page. We're just looking for magnitude. So I don't need that. I need ILB is equal to 2kx minus mg. So B is 2kx minus mg over LB. So this becomes 2 times 500 times 0.05 minus 2 times 10. The length is 45 centimeters, so 0.45. The B, what am I doing? I need an I instead of what? B. So that's I, and that B goes away. So that IL comes down. So that's the L. The I is 0.3. And so that gives us (222.22 Tesla), which is insanely huge. But back then, I mean, this problem came from 2010. I did not care a lick about numbers that made sense. I mean, largest B fields that we can produce on the order of 8 to 10 at most. 222 is like, I don't know what that is, but that's the number. Big deal. And so that's an example of forces working on wires and you having to, I mean, it's a classic. I had no idea that what I had written there, this was a hybrid problem because I had to understand vertical forces, magnetic forces on a wire. I had to understand springs. So there was a lot of stuff going on that I didn't have a name for it. So we've effectively covered all of problem set 4, everything that we really need to do in terms of theory. Problem set 5 material, I can knock that out in an hour. That's no big deal. And then problem set 6 is just me being mean and trying to figure up stuff. So today and tomorrow we'll finish it up if we don't have enough time, but today we're going to start with the idea of magnetic induction. And just as a Kirchhoff's law is going to show up on the test, a problem about magnetic induction is going to be on the test as well. Magnetic induction, the best example are generators. If you've ever played with a toy generator, there's all sorts of things. You can have like a hand cranked flashlight or a hand cranked radio. And what is that? Is that in the inside the generator, there are all these wires coiled, and inside there's a series of, I'm doing the drawing no justice, there's a series of magnets, and so the magnets move by the wires, and current is produced. You turn the crank, and really, if you've ever, you looked at, I've been there before. Actually, if you've seen the movie Transformers, where they have the super secret base in Hoover Dam, and in Hoover Dam they have all these big mechanical generators. The water passes by the turbines and the generator turns, and really what's happening is that the water is turning this big magnet past all these wires, and what's happening is that you're creating a potential difference, you're creating current, stuff like that. The energy of the moving water is being created or being converted into energy, electrical energy. An important thing that we need to talk about is revisit the word normal. And we're not talking about normal as in opposite of abnormal or strange. We're talking about the mathematical term for a normal vector. Normal is perpendicular to the surface. So if this pin was a vector, the normal vector to the surface of the Elmo is this. The normal to my hand at that point is this. So, and as I move my hand, the normal direction changes. So the normal is basically whatever is perpendicular to whatever surface we're dealing with. And it's, in most of our world, like for torque, we're familiar with the fulcrum, where we know about the force, we know about the distance from the fulcrum to the force, and actually that's a horrible sketch. The key part and what we did throughout 213 is that the force and that distance vector, the force vector and the distance vector were perpendicular. In a force on a wire, the B vector was perpendicular to L, whatever L direction or current, actually it's more about the current direction that we're interested in. In lab, it's the current balance lab. Part 3 shows the angle dependence. In our happy little world, the current and the B field are perpendicular. But in lab situations, in real world situations, it's not always the case. It's more like ILB, I think they have it as sine theta, such that if the current vector and the B field vector were both in the same direction, this theta is equal to 0. In this particular direction, if I and B are perpendicular, then theta is equal to 90 degrees. So if sine of 0 will give you 0, the magnetic force is equal to 0. For that situation, the magnetic force is ILB. And what they're going to show you is that given a theta, you're going to plot force. What they're going to have is they're going to have a coil where you can rotate the angle or change the angle of the wires with respect to the B field. And what you'll do is you'll see something like this. You'll see a sine or cosine wave. And something like this. It depends on how they set this problem up. But the key part is that the current and the B field have to be perpendicular. Now, coming back to what we have here. There is a couple of words that we need to introduce, and we'll introduce both of them right now. There is something called electric flux, which we don't really use, but might as well get the terminology out. And then there is magnetic flux. Flux, they use capital Phi as it. For electric flux, they use EA. For magnetic flux, or I'm sorry, E, just E, and magnetic flux is B. So electric flux, Phi sub E, magnetic flux, Phi sub B. The electric flux, by definition, is E times A. And then this is B times A. Now, the way that they have this set up is that it is actually cosine theta for both of these. And what they do is in this particular case, this is the surface. The B field is perpendicular to the surface. And if the surface is like this, the normal line to the surface is that direction. The theta in this case is 0 degrees. Theta is the angle between the B and normal. The B in the normal line. So the way that we set this up so that it's perpendicular, and so perpendicular gives you full strength, so that's why we use sine. Here, we're comparing the angle between the B field and the normal. So we need the function to be full strength when theta is equal to 0. How do we get that? Cosine theta. And so this covers situations where if we had the surface and the normal, and the B field was like this, then that angle would be theta. Now, the only times that we're really going to have to deal with the angle is for stuff like this in the lab. For class, we're not going to deal with it all that much. You should be able to identify the equation and that it's cosine for this. What's the angle that it's comparing itself with? But in terms of 214, that theta will always be 0. So the magnetic flux will be B times A. We don't have to worry about it. So definitely in problem set 5, the magnetic flux is always going to be B times A. I haven't done anything other than that, so now's not a good time to start. If I had an area A and there was a B field out of the page, and let's say the area was 2 square meters and the B field was 1/4 Tesla, the magnetic flux would simply be B 1/4 times 2, or 0.5 Tesla meters squared. So magnetic flux units are Tesla meter squared. So understand that the units, there's no cute word for that. It's just Tesla meter squared, and that's it. So if it's a circle, the area is pi r squared. If it's a square, just whatever the lengths are. And the thing that I'm looking for is the change in magnetic flux with respect to time. Which means that it's the change of the product BA with respect to time. Now, the thing that I'm going to do for the next, I don't know, couple of minutes, you guys are human. You should be able to know calculus. I really think we should be able to teach calculus in this class. Problem is, Hume Hall doesn't agree, but I believe in you guys. In this particular step, the best way for me to show you the equations that we're going to use is to use one little thing from Math 262. That's called the chain rule. You don't have to know it. All you got to do is just sit back and watch it. For the people who've taken the course, they know what I'm about to do. When you're taking a derivative of a product, you end up with this. Ooh, this is so hard. You get that. So the change in magnetic flux with respect to time is the sum of those two things. One is the B field times the change in area with respect to time. The other one is area times the change in magnetic field with respect to time. Over here, B is constant. Over here, A is constant. I know, it's just oppressively hard. What I've done right here is I've broken the problem into two sub-problems. We're going to do one of two different things. One is, similarly, this is like problem 2. You have a circle and you have an external, this is a wire, not extra, external changing B field. And so this changing, there's a changing B field around and in and throughout this wire. And there is another problem, and this is similar to problem 1 on problem set 5, is that you have a bar. The bar is moving at a constant rate. There is a magnetic field in this region that is constant B. A is changing. Over here, the area of the loop is constant. Over here, the area is changing. Over here, the B field is changing. Over here, the B field is constant. So what these two major problems are is really they're the extremes of this. We are not going to do problems where you're going to have to do both of these at the same time. You're either going to do a changing B field with a constant A or a changing A with a constant B, not both. The other thing that, I gotta have some mystery in this, is on test 2, one of these is gonna be the second problem. The first problem is Kirchhoff's law. The next one is one of these two. How do I figure it out? I typically flip a coin. The other thing that I promise you is, let's say this one is on the test, that one will be on the final. If that one is on the test, this one will be on the final. So we got to understand this. Now I've set up this magnetic flux and I've talked about the change in magnetic flux. So d phi b dt will either be b dA dt or d phi b dt is a dB dt. It's got to be one of those two. Now, what's the important thing? The important thing is that according to Faraday's law, that the change in magnetic flux with respect to time, the negative of that, is that. Now that's the epsilon sub mf, or as I like to call it, electromotive force. Electromotive force, similar to what's another thing, or what's something else that can give an electromotive force? A battery. What are the units of electromotive force? Volts. Good. So this sets it up, which means that you can write it like this, that the current is the electromotive force divided by the resistance of whatever that wire is or whatever the resistor is. So you can say that current is either B over R dA dt, or I is equal to A over R dB dt. So this is one of the stuff. Now what we're going to do is we're going to work through both types. And after this, I mean, we'll be done by 11 and a half an hour. But when I get done with this, you'll be good to go. The first thing we're going to do is we're going to do the circle problem. So we have a wire. The radius is 0.2 meters. The B field is 2 Tesla out of the page at time equals 0. The B field is 4 Tesla out of the page at time equals 20 seconds. The resistance of the wire, big R, is 2 ohms. The first thing I want to know is, what is the magnitude of I? We'll add more to this problem in a little bit, but we got to go over the basics. So you have an external changing B field. How is it changing? Well, dB dt is just the initial B field, or I'm sorry, the final B field minus the initial B field divided by the change in time, t. In fact, probably the best thing to do is to just write d delta B delta t. It's a consistent change, so this number, delta B delta t, we can also say is dB dt. So this gives you 2 divided by 20, or 0.1 Tesla per second. So we used kind of a variant of average velocity to get the change. I know that the current magnitude is the electromotive force magnitude divided by the resistance. The electromotive force, the area is constant, but the B field is changing, so that means we're using dA dB dt over resistance. Now, dB dt is just 0.1. So this is pi r squared. dB dt is 0.1. Resistance is 2. So the current flowing through this thing is 0.00628 amps, or I'm going to say 6.28 milliamps, so that the number looks a little bit more current. So the current flowing through the resistor is 6.28 milliamps. And so this is how you do it when you just get to just get the magnitude. If I said, what's the magnitude of the current flowing through it? You just crank that out and boom. Now comes the tough part, the physical science part of it, the rationalization through this whole thing. What I've done, the problem that I have is that we don't have enough time really We may have time in the review lectures, but what I'm going to do now is discuss why is the current for this wire flowing in a particular direction. What's the reason behind it? And what we've got to do is understand Lenz's law. And Lenz's law is responsible for the negative sign in Faraday's law. That electromotive force is negative d phi b dt. That guy, Lenz's law. And let's go into detail about why that negative sign is in there. I prefer not to use it when in multiple choice questions. If I go identify Faraday's law, you use the one with the negative sign. When you're dealing with problems, what I want you to do is play with the magnitudes, leave the signs out of it, and then I want you to rationalize what's going on. In this particular case, and actually what I'm going to do is I'm going to draw a bigger picture. So the B field initially is out. The B field final is also out. The way that I think of this problem is I treat magnetic flux as having a direction. Magnetic flux is B times A. So the initial magnetic flux is out of the page. Magnetic flux is parallel to the B field. So the initial magnetic flux is out of the page. The final magnetic flux is out of the page as well. Because the B field is out, the initial B field is out, therefore the initial magnetic flux is out, and the final magnetic flux is out. If the B field initially is out and the final B field is out and bigger, because we've said that B is greater than B naught, the change in B with respect to T is also out. The B field went from 2 to 3 to 4, which means that the change in B, in order to get the B naught to go from out to even more out, that change in B has to be out as well. If that change in B is out, then the d phi b dt is out as well. So the dB dt is parallel to d phi b dt. And now we're going to get to Lenz's law. Lenz's law is when a loop of wire encounters an externally applied change in magnetic flux, the loop will experience an induced current this current, and you know how I hate writing, this current produces an induced magnetic flux that opposes or is anti-parallel to the external phi sub b. A lot of words. Really what's happening is a changing magnetic field produces a changing flux. This changing flux is seen by the wire. The wire goes, I don't want any part of this. And an induced current is produced to oppose this. So when you see a d phi b dt, now traditionally with parallel, I just draw this. With anti-parallel, I draw the little arrow signs to definitely show that it's anti-parallel and opposite. To the d phi b dt that is induced. And I'm going to do the induced parts in red. So the induced has to be in. The magnetic field is out. The magnetic flux is out. It increases, so the change in magnetic flux must be out as well. So the change in magnetic flux with respect to time that's induced must be in. In order to get this, the induced B field must be in as well. Be induced parallel to d phi b dt induced. In what direction is the current, or what is the direction of the current that produces a B field that is in? The induced current, we use our wrap rule, that induced current in this particular case must be clockwise. What happens is that the B field is out. The change in flux is out. The induced is always opposite of this, so it's in. The induced current, or the induced magnetic field, must be in as well. The only way to get this to happen is for a clockwise current. To get it into the page, you have to have a clockwise current. To get it out of the page, you must have it counterclockwise. And really quick, while we're talking about all this, because I know it's going to show up, in the lab, in 214, we just use single loops. In 224, in order to get the job done, they got to use coils. Coils are just the total loops that they have. If you've got 10 loops, Let's say your magnetic induction was 1 Tesla meter squared. If you had 10 loops of that, just multiply it by 10. And so there's just an extra factor of N. I have to mention that now because I know that you guys may use it in the lab this afternoon. But in this particular case, the way that this thing is set up is the current is producing a clockwise current. And this is the gist of one of the problems that we're going to do. There are 2 of them on problem set 5. What we're going to do is tomorrow and then Friday and Monday is go over the permutations. There are 4 permutations to this type of problem, and we're going to go through them all. We will rationalize what direction is the current for all the different variants tomorrow and Friday. The other one is the moving bar. Which is, in my opinion, a slightly more interesting problem. The moving bar, you've got wire that stretches on forever to the right. Connecting the wire is a resistor and more wire. The B field is in this particular region, in the dotted red region. And it doesn't really matter, but the B field well, it does matter in a way. B field is out, and the B field has a magnitude of 0.5 Tesla. There is a bar resting on this wire, and the bar has a length of L. The bar is moving with a velocity of V. Bar length 2 meters, velocity 10 meters per second. The resistance is 2 ohms. And what happens is, you've got this region here. And that is area A. Now, is the area that's shaded green, is that area getting bigger or smaller because the bar is heading to the right? It's getting bigger. If the bar was heading to the left, the area would be getting smaller. The question is, what is I induced, and is the current clockwise or counterclockwise? These wires stretch on forever and don't join up. This completes the circuit, and the circuit is this. But the bar moves. The bar is a moving bar, which means that we have a changing area, which means that we are going to use that I, which is the electromotive force divided by resistance, is B dA dt over R. We're going to use that. The problem that we have is that we don't know what the changing area is. In fact, I could give you, let's just say I'm very nice, and I say that X is, at that particular moment, 0.4 meters. It doesn't really matter, and I'm going to show you why. Remember how we used the chain rule before to get this. We're going to do the chain rule to get this. That d dt of area is equal to d dt of Lx, which means that this is x dl dt plus L dx dt. When looking at this, does the L change? Does the length of the bar change? No, remains constant. So that is 0. So we're left with L dx dt. And what's another way of saying dx dt? What's the change in position with respect to time? Velocity, yes. So this becomes LV. Because I gave you V, you don't need X. You need the change in X. So this becomes I BLV over R, which makes it 0.5210 over 2, which means those cancel and I'm left with 5 amps. And so that is the induced current in the problem. Now to determine the direction of the current. Now what I'm going to do is I'm going to draw it bigger. Since we used induced is red last time and B is external, the B field, we're going to keep it consistent. So the B field in this case is out. The velocity, and we have 8 minutes, is to the right. And what I'm going to do is I'm going to briefly walk through it and then we'll end it, and then tomorrow we'll do it in more detail. If the B field is out and this is the region, the magnetic flux is out as well. The B field and the magnetic flux are always parallel. The bar is heading to the right. That means that the window is getting bigger. And if the wind is coming out of the page and the window is getting bigger, there's more wind coming through the window, which means that the d phi b dt is also out of the window. If the bar was heading to the left, the area would get smaller and those would be opposite. If the bar is going to the right, they are parallel. If the bar is going to the left, they are anti-parallel. Lenz's law takes over and goes, I can't stand this change, so it induces a magnetic flux which is into the page. The induced magnetic flux, change in flux, is produced by a magnetic flux that is into the page as well, and the only way to get this to go into the page is to induce a current that is clockwise. And so that lets us know what the B field is, or I'm sorry, the direction of the current. The last thing that we need to figure out, I've got a bar, it's got current, it's moving through a magnetic field, which means that there is a magnetic force on the bar. The magnetic force on the bar is ILB. The I is 5, the L is 2, the B field is 0.5. So there is a 5 Newton force on that bar that will try to slow it down. What direction is the force? Well, I is towards the bottom of the page, the B field is out, so IB forces to the left. That magnetic force wants to slow it down because the force is opposite of velocity. To keep V constant, an external force Fe is applied. Fe is equal to Fb, but opposite in direction. So in order to keep this bar constant, the Fe must go in that particular direction. And what we're going to do over the next couple of days is we're going to work through all the permutations, and you will see that the Fb will always be anti-parallel to the velocity. And we'll work through it. It's not something that you can just blatantly say, but when you do the problems and you end up with magnetic forces opposite of velocity, you know you're going in the right direction. That's it. Have fun in lab.